Hello dear students, I'm going to discuss various aspects of nuclear radioactivity, broadly divided into different units and subunits. Initially, I will discuss in the first unit types of nuclear radiation. Then in the second unit, I will discuss the theory of radioactivity. In the third unit, I'm going to discuss the interaction of nuclear radiation with matter. And in the final units, I'm going to discuss few elementary types of detectors like Geiger-Müller counter, which are used in your MSc nuclear physics laboratories. So this course would be divided into different chapters. Each chapter would be divided into different subheadings, and each subheading would constitute an independent video, and you can click on the link that would be given in the description box if you want to access any particular topic from any particular chapter. This course would be beneficial for you if you are taking your BSc in physics and you are taking up a course or a paper on nuclear physics. Similarly, in MSc also, it is going to help you in your laboratory as well as in your theoretical paper. So basically, this is a course on nuclear radiation, types of nuclear radiation, the theory of radioactivity, different types of interaction of nuclear radiation with matter, and few important nuclear radiation detectors. Now, I'm going to start with the first unit, and in this first unit, I'm going to discuss the types of nuclear radiation. So in this particular subsection, I'm going to discuss only the types of nuclear radiation. What are the different types of nuclear radiation, and what is the properties of these different types of nuclear radiation. So here you can see there is a beta particle coming out from a nucleus of carbon-14 atom. So here is a carbon-14 nucleus which has got 6 protons and 8 neutrons, and it converts into nitrogen 14, which constitutes 7 protons and 7 neutrons, and in a process it emits a beta particle along with other radiation. We will discuss what are the other types of radiation that come out along with beta particle in the later sections. But for now, what is actually happening is that a neutron is converting into a proton. So you can see here the proton number is increasing from 6 to 7 as carbon converts into a nitrogen. And in the process, due to conservation of charge, a beta particle, which is a negatively charged electron, is produced. So primarily these radiations that come out, they come out from the nucleus or from the atom. And they are conveniently categorized into 4 general types as follows. Number 1 is the charged particulate radiation. Basically, radiation which are charged and particulate or particle in nature. And there are 2 types of these radiations. So number 1 is the fast electrons, and the second one is heavy charged particles. And also there are uncharged radiations that come out in the form of electromagnetic radiation and neutrons. So what are the fast electrons? Fast electrons are called the beta particles, which can be either positive or negative. So beta particles are either electrons or positrons. These are emitted in nuclear decays as well as other processes like nuclear fission, etc. So they are highly energetic particles that come out and have a very deep penetrating power. The other types of particles that can come out during a nuclear decay are the heavy charged particles. So these are basically all positive ions which are coming out, or positive nuclei that are coming out with atomic mass of 1 or greater than 1, such as alpha particles, proton, or fission products. Then we have the electromagnetic radiation, which includes the X-rays which are emitted by the atoms, in which the atomic transitions take place between the different shells of the electrons in the atom, or these can be gamma rays that come out from the transition of the within the nucleus itself. So basically, the change in the energy in the nucleus itself results in the emission of gamma rays. Then also we have neutrons that can come out in various nuclear processes. These are the final and the major category that comes out, and these are further subdivided into slow neutrons and fast neutrons. So either they are coming out with a very low speed, or they can come out with a very high speed, and different types of processes which we will discuss later in the different units, subunits actually, of this chapter, and then you will understand more clearly what are the different types of nuclear radiations that come out and from which kind of processes they come out. So the energy, basically when we talk about the energy of radiation, it spans a very wide range from 10 electron volts to 20 mega electron volts. So almost 6 order of magnitude is the range of energy that comes out when we talk about nuclear radiation. So now we will discuss, whenever we are talking about sources which produces nuclear radiation, the most important thing is how to construct a source, in what geometry one should construct a source. That is the important thing. So the thickness of the source is a very important criteria to consider when we talk about constructing a source. So the thickness of the source is very important, because as we will learn later, nuclear radiation interacts with the surrounding medium. So basically the surrounding medium constitutes the air or some solid material which covers the source, but it also interacts with the source itself. So since material absorb radiation, the source material will also absorb radiation. So the thickness may lead to self-absorption. If the source material is quite thick, then almost all of the radiation can be absorbed by the source material itself. So we have to consider what should be the thickness of the source when we are making the source and we are using it for any experiment. So the thickness of the source can be between micrometers to 1/10 of a millimeter, depending upon the energy of the radiation and its penetrating power. So basically a source can be in the micrometer range, that is 10 raised to the minus 6 meters, or 1/10 of a millimeter. Between these two ranges it is possible to make a source, and it depends upon the energy of the radiation. If the energy of the radiation is small, then we have to make a very thin source of the micrometer range. And if the energy of the radiation is high enough, then in that case we can make a thicker source, like up to the range of 1/10 of a millimeter. So we can consider some elementary examples, like a beta particle is generally more penetrating compared to heavy ions like alpha particles. So beta particles are more energetic and more penetrating. So higher is the penetrating power, more can be the thickness of the source. So there are two important quantities which are used when we talk about nuclear radiation. Number one is the radioactivity, and the radioactivity is defined by the term called activity, and the activity is defined by this particular equation here, which is dN by dt is equal to minus lambda n. So this quantity called dN by dt is called the activity, and this is equal to minus lambda n. Now what is this dN by dt? It is the rate of change of number of nuclei which are decaying with respect to time. So it is the rate of change of n with respect to t, which is represented by dN by dt. So in 1 unit of time, if n number of units of n number of nuclei are decaying, then the activity will be given by dN by dt, and this actually is equal to minus lambda n. So basically this dN by dt is proportional to the number of nuclei which are present in the sample. So the number of nuclei is high, then the rate of decay is also going to be high. And the proportionality constant is called the decay constant, which is the lambda. So higher is the decay constant, higher is the activity. So decay constant is basically tells you how radioactive a substance is. And what are the units of activity? So the first unit that we talk about is the Curie, which is 3.7 into 10 raised to power 10 disintegrations per second. So basically in 1 second, if 3.7 into 10 raised to power 10 disintegrations are taking place, then we say that 1 Curie of radioactivity is produced by the sample. Now why is this queer number used for the unit of radioactivity? Now why it is so? Because initially when the radioactivity was studied, the scientists found that 1 gram of pure radium-226 produces this much of activity. So 1 gram of pure radium is basically producing 3.7 into 10 raised to power 10 disintegrations in 1 second. So that was considered to be the standard unit of radioactivity. But later on, when the SI units were introduced, it was the becquerel that was considered to be the SI unit. And the SI unit becquerel means 1 decay per second. Simply 1 decay per second means 1 becquerel of radiation or the radioactivity is coming out. And 1 becquerel turns out to be equal to 2.703 into 10 raised to the minus 11 Curie. The second important quantity is the energy, and its units are electron volts. So what is an electron volt? So whenever we're talking about radiation that is coming out, it is coming out with some energy, and that energy is generally measured in the form of electron volts. So if you have a potential difference of 1 volt, an electron travels this potential or covers this potential difference, 1 electron, then it gains an energy of 1 electron volts. So that is the definition of electron volts. So you can see here, so in this diagram, 1 volt of potential difference is basically produced between the 2 electrodes, and an electron is allowed to travel from one electrode to the other electrode. So basically it travels a distance of 1 volt between two ends. So a potential difference of 1 volt is covered between the two ends by the electron. So it gains an energy of 1 electron volts in this process. Similarly, if you have a 1000-volt potential difference, and electrons are allowed to travel this potential difference from one end to another, then it will simply gain a potential energy of 1000 electron volts. So basically this is the energy, that is the unit of energy is defined like this. The other unit of energy is the SI unit of, which is the joules, which is used in common day-to-day work and power experiments that we do in normal macroscopic world. So in the macroscopic world, the joules is a reliable unit, but in the microscopic domain, joule is a very large unit. So you have to use smaller units like electron volts, and 1 electron volts turns out to be equal to 1.602 into 10 raised to the power minus 19 joules. And other smaller units like femtojoules can also be used, and a femto means a factor of 10 raised to the power minus 15. So a femtojoule means 10 raised to the power minus 15 joules. So basically here we have defined two different types of different units that are used in the study of radioactivity, which is the radioactivity and the energy.